Hello everyone. We are continuing with the thermochemistry part. In the previous lectures, we have discussed some of the enthalpy changes in different types of reactions. Now we are continuing with this enthalpy change in a chemical process. So starting with this, we'll take up enthalpy of combustion. The symbol is delta H combustion. Now first of all, let's define what is combustion. So combustion is the complete oxidation of a substance to its highest oxidation state in presence of oxygen. So the element should be oxidized to its highest oxidation state. So when 1 mole of a substance is completely oxidized in presence of excess oxygen, how much energy is evolved, given out? That is always defined as enthalpy of combustion. So combustion process is always exothermic. Energy is always evolved during a combustion process. So one thing that we have to keep in mind is combustion is complete oxidation in presence of excess amount of oxygen when the element is oxidized to highest oxidation state. And second thing, enthalpy of combustion is always and always exothermic process. Energy is always given now, so the sign of enthalpy change for this process will always be negative. So we say this is heat released when 1 mole of a substance is completely oxidized in presence of excess oxygen. So element should be completely oxidized to its highest oxidation state. So we said this is heat release, so it is always an exothermic process. So delta H combustion. So enthalpy of combustion will always be negative. Even if it's not mentioned in the question paper or in the problem, that you have to assume that this delta H should always be negative. You have to use the negative sign for the calculation point of view. That is what we call as enthalpy of combustion. So let me look at this. We have looked at this. Carbon solid combines with oxygen. This is a combustion process. So for this, look at this. Since we have a reaction, so enthalpy of reaction for this reaction of carbon plus oxygen to give you carbon dioxide. This enthalpy of reaction is equals to enthalpy of formation of carbon dioxide, because 1 mole of carbon dioxide is formed from constituent elements. So this enthalpy of formation of carbon dioxide is equals to the enthalpy of combustion of carbon. So carbon, combustion of carbon to give you carbon dioxide. So enthalpy of combustion is equals to, for this reaction, enthalpy of combustion is equals to enthalpy of formation of carbon dioxide, which is nothing but the enthalpy of reaction. Similarly, look at this. N2 plus oxygen, this gives you N2O5. Suppose we have this reaction, this is nitrogen gas combined with oxygen gas to give you nitrogen pentoxide. Now in this reaction, look at this, there is a formation of N2O5 nitrogen oxide. So this enthalpy of reaction, again यहाँ पे look at this enthalpy of reaction is equals to enthalpy of formation of N2O5, because in this reaction 1 mole of N2O5 is formed. So this is equals to enthalpy of formation of N2O5, which is equals to the enthalpy of combustion of nitrogen. This is also a combustion process, but look at this, fluorine gas combines with oxygen gas. So oxygen being less electronegative, this gives you OF2. Suppose a OF2 is formed. Now if you look at this, fluorine, initially this was 0 oxidation state, now this changes to -1, whereas the definition says should be oxidized. But in this reaction, fluorine is reduced from -1 to 0. So this process is not a combustion process. So combustion means elements should be oxidized, and that too in the highest oxidation state. That should be the combustion. So this reaction is a reaction, but this is not a combustion process. So for this, enthalpy of reaction can be defined in terms of combustion. Similarly, suppose we have CH4 gas combines with oxygen gas, when this gives you carbon dioxide gas plus H2O. In this reaction, carbon is oxidized from -4 to +4. So we say this is a combustion process. So all this process, the enthalpy change for this process. Suppose this is for this reaction, enthalpy of reaction. This is a reaction, so we say this is enthalpy of reaction. So for this, enthalpy of reaction will be equals to the enthalpy of combustion of CH4. So this is how we define enthalpy of combustion. Now, if suppose enthalpy of the combustions of the reactants and the products are given, then how to define the enthalpy of reaction? So we have the relation between enthalpy of reaction and the enthalpies of combustion. So the relation is enthalpy of reaction is equals to the summation of the enthalpies of combustions of reactants minus the summation of enthalpies of combustion of the products. So this gives you the relation between enthalpy of reaction and enthalpy of combustion. So normally we define enthalpy change as product minus reactant, but for this enthalpy of reaction in terms of combustion, this is combustion of reactants minus combustion of products. This is for those reactions in which the enthalpies of combustions of the reactants and the products are given in the question, and we have to find the enthalpy of reaction. So for this we can use this relationship. So this is one of the relationship in which we have to define enthalpy of reaction by use of the enthalpy of combustion, that is for the reactants and the products. Now from this enthalpy of combustion, we define one more term, that is the calorific value. Or fuel efficiency. That means when we burn a particular substance, so how much energy is reduced, that is defined as the calorific value. So the more is the calorific value, more efficient the fuel will be. Means on burning 1 gram of the substance, a more amount of energy will be released. That becomes a better fuel. So we have to define this calorific value from this enthalpy of combustion data. Now this calorific value is defined as the energy released during combustion of 1 gram of fuel. So how much energy is released during the combustion of 1 gram of the substance, that is defined as the calorific value. So this is energy release during the burning of 1 gram of a substance. So that is, so therefore calorific value CF, this is defined as the enthalpy of combustion. Because enthalpy of combustion, this is defined for 1 mole of the substance. Because enthalpy change is always defined for 1 mole of the substance. So we divide this enthalpy of combustion divided by the molar mass. So enthalpy of combustion divided by molar mass, this gives you the energy released during the burning of 1 gram of the substance. So this is what we call as calorific value. So this value defines the efficiency of fuel. So more the calorific value, more efficient the fuel will be. So if you suppose we have to compare the efficiency of fuels, then we have to find the enthalpy of combustion per gram of the substance. So once we have this, we can easily compare. So the one which have the larger value of calorific value will be a better fuel. So this is enthalpy of combustion. So first thing is we have to define what is a combustion. Second, combustion is always exothermic. Then once we have this combustion, how to relate this combustion data with enthalpy of reaction, provided the enthalpies of combustion of reactants and the products are given to you. Then from this we have to define the calorific value or the fuel efficiency or the energy efficiency. So this is combustion per gram of the substance. So this is enthalpy of a combustion process. Then we have enthalpy of neutralization. The enthalpy of neutralizations. As we know, the neutralization is a reaction of an acid with base to give you unionized water and the salt. This is what we call as neutralization process. So how much energy is involved during the neutralization of an acid with base or a base with an acid, that is defined as the enthalpy of neutralization. So neutralization process this is defined as the combination of H plus ion with OH minus ion. The reaction of H plus ion with OH minus ion is hydroxide ion, which results in the formation of unionized water. This reaction is defined as the neutralization process. So during the neutralization process, H plus ion will combine with OH minus ion to give you unionized water. So if you look at this reaction, if we take 1 gram equivalent of H plus N. So 1 gram equivalent of H plus N with 1 gram equivalent of OH minus N. So when 1 gram equivalent of H plus N combines with 1 gram equivalent of OH minus N, resulting in the formation of unionized water, how much energy is released? That is defined as the enthalpy of neutralization. So this is the quantity of H plus N and OH minus N that has to combine, and energy release in this process. This energy release, this is defined as enthalpy of neutralization. This is always negative. So neutralization is always exothermic. Neutralization process is always exothermic, energy is released. So look at this definition carefully. 1 gram equivalent of H plus N has to combine with 1 gram equivalent of OH minus N, which results in the formation of unionized water. So how much energy is released? That is defined as the enthalpy of neutralization. That means 1 mole of H plus N plus 1 mole of OH minus N release. Then we said this is enthalpy of neutralization. Now look at this. Suppose we have 1 mole of strong acid plus 1 mole of strong base. So we have a combination of 1 mole of strong acid plus 1 mole of strong base, means H plus N is coming from strong acid and H plus N is coming, OH minus N is coming from strong base. Then the enthalpy of neutralization of such type of reaction, means enthalpy of neutralization when 1 mole of H plus N from strong acid combines with 1 mole of OH minus N coming from strong base. The value is always a fixed quantity, that is 13.7 kilocalorie per mole, which is equals to 57.3 kilojoule per mole. So this is always a fixed value. So enthalpy of neutralization of a strong acid with a strong base is always a fixed value, that is 13.7 or 53.3. Now as I told you, this enthalpy of neutralization is always exothermic process, so we should use this negative sign. Minus 13.7 kilocalorie per mole minus 57.3 kilojoule per mole. Now the question is, what are strong acids? Strong acids, like look at this, we have sulfuric acid is a strong acid, nitric acid is a strong acid, we are looking at HClO4, perchloric acid is a strong acid, HiO4, this is a strong acid. These are strong acids. Weak acids, like look at this, HCN is a weak acid, organic acids, these are weak acids. Strong base, we have look at this, sodium hydroxide, potassium hydroxide, cesium hydroxide, calcium hydroxide, etc. These are known as strong base. Weak base, we have look at this, ammonium hydroxide, etc. So strong base means which can dissociate to almost 100%. Weak acid means whose dissociation is incomplete, so the quantity of acid H plus N will be less than the expected. Similarly, strong base, the one which gives you full ionization. Weak base, the one which does not give full ionization. So but if we have a combination of strong acid, weak base. So we have strong acid plus weak base, or we have a strong base plus weak acid, or we have a combination of weak acid plus weak base. This was strong acid, strong base, for which the value is always a fixed quantity. Now, if we have these three combination, strong acid, weak base, strong base, weak acid, weak base, the enthalpy of neutralization of such type of acid-base reaction is always less than this minus 13.7 kilocalorie, or which is less than minus 57.3 kilojoule per mole. That means for this combination containing one weak acid or weak base, or both are weak acids and weak base, the enthalpy of neutralization is always less than the enthalpy of neutralization of a strong acid and strong base. So question is why? So the reason is, this being a weak acid or weak base which is not 100% or fully ionized. So during the course of reaction, some of the energy released will be further consumed for ionization of the weak acid or weak base. So the reason is, the energy released during neutralization process will be consumed by the weak acid or weak base. Energy released during the neutralization process will be consumed by the weak acid or weak base for further ionization process. So out of the total energy released, some of this released energy will be consumed by this weak acid or weak base for further ionization. Hence, the enthalpy of neutralization of these three combination of acid base will always be less than the maximum value, that is the enthalpy of neutralization of strong acid by strong base, that is minus 13.7 kilocalorie per mole or minus 57.3 kilojoule per mole. So this we have to keep in mind. So that means, suppose we have the reaction between sodium hydroxide and sodium hydroxide and acetic acid. So look at this. This is organic acid, so which is a weak acid. This is strong base. So therefore, the enthalpy of neutralization will be less than this value, minus 13.7 kilocalorie per mole. Similarly, take this case, we have this ammonium hydroxide reacting with sulfuric acid. This is a weak base, this is a strong acid. Similarly, look at this, we have ammonium hydroxide plus acetic acid. This is weak base, this is weak acid. So all for this combination, enthalpy of neutralization is always less than the maximum value. Then the question is how to define the enthalpy of neutralization, or from calculation point of view, what value we have to use. So for calculation point of view, the enthalpy of neutralization, enthalpy of this neutralization is always equals to minus 13.7 plus enthalpy of ionization of the component. Or this is in terms of kilocalorie per mole, or we can say this is minus 57.3 plus enthalpy of ionization. So this is in terms of kilocalorie, this is in terms of kilojoule, because we have two different values. So this ionization is always positive. That means if this is positive, so less amount of energy will always be released during neutralization of this strong acid weak base, strong base weak acid or weak base. So we can use this equation to find the enthalpy of the neutralization. So enthalpy of neutralization is given to you, then we can define what is ionization. So look at this. For strong acids and strong base, this enthalpy of ionization is always equals to 0, so we have the maximum value. So for weak acid and weak base, enthalpy of ionization is always a positive value. In some energy we have to give so that this undergoes further ionization. So this is enthalpy of neutralization. So look at this reaction. We have look at this. 1 mole HCl reacts with 1 sodium hydroxide. Reaction of 1 mole HCl plus 1 mole sodium hydroxide. What is the enthalpy of neutralization for this? So look at this. HCl ionized to give you H plus N. So 1 mole HCl will give you 1 mole. Sodium hydroxide ionized to give you OH minus. So sodium hydroxide being strong base, so 1 mole sodium hydroxide will give you 1 mole. So look at this. There is a reaction between 1 mole of H plus ion with 1 mole of OH minus ion. So this value, strong acid, strong base, 1 mole, 1 mole. So enthalpy of neutralization will be minus 13.7 kilocalorie per mole. But look at this. If I say 1 mole HCl plus 2 mole sodium hydroxide, then the question is, what is the enthalpy of neutralization of this? When I use 1 mole of HCl, so HCl will ionize to give you H plus N, so 1 mole HCl will give you 1 mole H plus N. 2 mole sodium hydroxide will give you 1 mole is giving 1 mole, so 2 mole will give you 2 mole. So now look at this. We have 1 mole H plus N in solution, 2 mole OH minus N in solution. Now this has to react. Now out of these two, this H plus N is the limiting reagent. That means out of the 2 mole OH minus N, 1 mole will be consumed by H minus N. The moment H minus N is fully consumed, the reaction will stop. No further reaction takes place. That means this being excess, 1 mole is left unused. So it means still we are reacting 1 mole of H plus N and 1 mole of OH minus N. So this value, enthalpy of neutralization, will again be minus 13.7 kilocalorie per mole. Take this, suppose we have 2 mole HCl combining with 2 mole sodium hydroxide. So HCl will ionize to give you H plus N, so 2 mole will give you 2 mole H plus N. Sodium hydroxide will give you OH minus N. 1 mole is giving 1 mole, so 2 mole will give you 2 mole. Now reaction is between 2 mole H plus N and 2 mole OH minus N. Then the enthalpy of neutralization is 2 times minus 13.7 kilocalorie per mole. because for 1 mole energy release is 13.7. So for 2 mole energy release will be twice of the value. Now take this, we have HCl 100 ml 0.1 molar is used, plus sodium hydroxide 100 ml 0.1 molar solution is used. So we have two solutions of HCl and sodium hydroxide. Now look at this, 100 ml and 0.1. So number of moles of acid will be equals to molarity into volume. So molarity is 0.1, volume is again 0.1 liter. So we have to convert this in terms of liter. So this is 0.01 moles of HCl. Similarly, number of moles of base sodium hydroxide is again 0.1 into 0.1. So that is 10 to the power minus 2 mole. So again look at this, 1 mole of HCl will give you 1 mole of H plus N. So number of moles of H plus N will still be equals to number of moles of HCl, that is 10 to the power minus 2. Similarly, number of moles of OH minus N is equals to number of moles of sodium hydroxide, that is 10 to the power minus 2. Now we are reacting with 10 to the power minus 2 moles of H plus N and 10 to the power minus 2 moles of OH minus N. So therefore, the enthalpy of neutralization will be 10 to the power minus 2 into minus 13.7 kilocalorie per mole. So this is how we have to find the enthalpy of neutralization. I'll give you one more example. Look at this. Take this. We have H2SO4 plus sodium hydroxide. I take this 100 ml 0.1 molar and I take this 200 ml and 0.1 molar sodium hydroxide. Now these are mixed together, then what is the enthalpy of neutralization? So now it is number of moles of sulfuric acid is 0.1 into 0.1, so that is 10 to the power minus 2. Number of moles of sodium hydroxide is equals to 0.1 into 0.2, that is 2 into 10 to the power minus 2. Now look at this, number of moles of H plus N is equal to 2 times number of moles of sulfuric acid. So therefore 2 into 10 to the power minus 2 moles of H plus N. Number of moles of OH minus N is equals to number of moles of sodium hydroxide, that is 2 into 10 to the power minus 2. Now we are reacting with 2 into 10 to the power minus 2 moles of H plus N, 2 into 10 to the power minus 2 moles of OH minus N. So therefore enthalpy of neutralization is 2 into 10 to the power minus 2 multiplied by minus 13.7 kilocalorie per mole. Now the question is this part. So look at this reaction. We have this sulfuric acid. 1 mole of sulfuric acid gives you 2 moles of H plus N. So this is the reaction. So since 1 mole of sulfuric acid always gives you 2 moles, so the number of moles of H plus N is twice the number of moles of sulfuric acid. So we have used this relationship. So this is how we define the enthalpy of the neutralization process. How to calculate the enthalpy of neutralization process. Or I'll take you one combination here. Suppose we have looked at this, acetic acid combines with sodium hydroxide. We have looked at this. This is weak acid, this is strong base. Okay. When this acetic acid reacts with sodium hydroxide, suppose take this is 1 mole, this is 1 mole. So 1 mole acetic acid on reaction with 1 mole sodium hydroxide, heat released is minus suppose 49.7 kilojoule per mole. Then question says what is the enthalpy of ionization of acetic acid? Because we know this is a weak acid, we require some energy for its ionization. So question is what is the enthalpy of ionization of this value? We have this relationship, look at this. So enthalpy of neutralization is equals to minus 57.3 plus enthalpy of ionization. So therefore enthalpy of ionization is equals to 57.3 plus enthalpy of neutralization. So therefore look at this, heat release is 49.7, that is enthalpy of neutralization. So we have 57.3 plus, this is minus, so we can have this minus 49.7 kilojoule per mole. So this is the enthalpy of ionization of this weak acid, acetic acid. So this is how we have to use the relation to find the enthalpy of ionization. And if enthalpy of ionization is given to you, then we can also define the enthalpy of the neutralization. So one thing again I am reminding you, for neutralization process we have to define how many moles of H plus ion is reacting with how many moles of the OH minus ion. For 1 mole H plus ion, 1 mole OH minus ion coming from strong acid, strong base, the values are always fixed, that is the 13.7 or 53, so 57.3 energies per mole. So we have to use this to find the enthalpy of neutralization. Then we have enthalpy of some phase transition. Enthalpy of phase transition. Suppose look at this, we have enthalpy of vaporization. So we have look at this, H2O liquid is to be converted into H2O vapor. That means liquid is converted into the vapor form. So for this look at this, enthalpy change for this conversion of liquid to vapor, this enthalpy change is what we call as enthalpy of vaporization. So liquid is to be converted into vapor, so you have to supply energy, this is always a positive. Then we have enthalpy of fusion. Enthalpy of fusion means we have this, suppose I am taking example of water. So this ice is to be converted into liquid. Fusion of the melt. So on means solid will be converted into liquid. So we say vaporization process. Vaporization means liquid is to be converted into vapor. Fusion means solid is to be converted into liquid. So enthalpy change for this process, this is known as enthalpy of fusion. Now take the other way around. Enthalpy of freezing. So freezing means liquid is to be converted into solid. So suppose look at this, H2O liquid is to be converted into H2O solid, that is freezing process. So this enthalpy of freezing is always equals to the minus of the enthalpies of fusion. Both are in opposite directions, so energy will be same but sign will be negative. If one is heat consumption, the other one will be heat releasing process. This is enthalpies of phase transition. We can also have sublimation process. Enthalpy of sublimation. Sublimation means direct solid is converted into vapor without going through the liquid phase. So enthalpy of sublimation is always equals to enthalpy of fusion plus enthalpy of vaporization. So if fusion and vaporizations are given to you, we can add these two to give you enthalpy of sublimation. Then we have enthalpy of atomization. So as the name suggests, atomization, we are converting the elements into the corresponding atoms. That means, if suppose we have a solid state, element in solid state, this element in solid state is to be converted into the gaseous atom. So look at this, suppose we have enthalpy change during the formation of atoms from the constituent elements. So look at this, we have carbon solid, this is to be converted into carbon gas. So this process, conversion of these elements from its initial solid state to the gaseous state, this we say this is enthalpy of atomization of carbon, or simply we can say this is sublimation process also. Similarly, look at this, suppose we have hydrogen gas. This hydrogen gas is to be converted into hydrogen atomic form. So we say this is enthalpy of dissociation of hydrogen gas or enthalpy of atomization of hydrogen. So hydrogen molecule is to be converted into atomic hydrogen. So this is how we have to use. This is enthalpy of dissociation of hydrogen or enthalpy of atomization of hydrogen. So various forms, various terms are used, so we have to pretty much sure how these terms should be related to each other. So many of the questions is enthalpy of dissociation of hydrogen, but question is what is the enthalpy of atomization. But question given enthalpy of dissociation, but in the problem we have to use as an enthalpy of atomization. So these are related to each other, so we have to be very careful. So these are some of the enthalpy change that we often comes into. Okay. Apart from this, we also have bond enthalpy, bond energy or bond enthalpy. Bond energy or bond enthalpy. Now this bond energy or bond enthalpy is defined as the average of the bond dissociation energies of a type of bond present in a given molecule. So this is the average of bond dissociation energies of a particular type of bond in a given molecule. So suppose, take this, we have this carbon, hydrogen, CH4, that is the methane. Now we have to define the bond energy of carbon hydrogen bond. So this bond energy of carbon hydrogen bond we have to define. Definition says this is the average of the bond dissociation energies of this carbon hydrogen bond. So how many bonds? 4 bonds. So therefore look at this, this is Suppose look at this, we have CH4. Now break this first hydrogen bond, so we have breaking of first carbon hydrogen bond. Suppose this is delta H1. Then we have, look at this, breaking of second carbon hydrogen bond. We have this delta H2. Similarly, breaking of this, we have plus hydrogen delta H3. Then the last bond, that is, so this is delta H4. So bond dissociation energy, that is delta H1 plus delta H2 plus delta H3 plus delta H4. Since we have 4 carbon hydrogen bond, 4 energy terms are involved for breaking of this carbon hydrogen bond. All these are hydrogen carbon bond, but there are different values. The reason is, this is CH4, this is CH3. These are 2 different entities. So we require different energies. So the total energy is this summation of 4 energies. So this bond enthalpy of one carbon hydrogen bond is 1/4, because we say average. So we have 4, take the average of this bond dissociation energy. So this is delta H1 plus delta H2 delta H3 plus delta H4 divided by 4. This is how we define the bond energy or the bond dissociation enthalpy. So once bond energy is given to you, then also we can define what is the bond dissociation enthalpy. So always this bond energy is defined in terms of the average of the bond dissociation. So this bond energy measures the strength of bond. If the bond energy is more, bond is stronger. If bond energy is less, bond is a weaker bond. So this is how we correlate bond energy or bond enthalpy with the strength of the bond. Now that we have laws of thermochemistry. Now we have 2 laws that governs thermochemistry, and the 2 laws, first law is Laplace and Lavoisier law. Laplace and Lavoisier law. Now this law says the enthalpy of formation of a given substance is always having same magnitude but opposition with the enthalpy of dissociation of the same element compound to give you the elements. So enthalpy of formation and enthalpy of dissociation of the same substance will have the same energy values but with opposite sign. Enthalpy of formation and enthalpy of dissociation. Enthalpy of formation and enthalpy of dissociation of the same species are always having same numerical value but with opposite sign. So enthalpy of formation and enthalpy of dissociation of the same space are always having same value but with opposite sign. So look at this example. We have this nitrogen, take this, we have H2 plus I2, suppose half mole when this gives you HI. So we have this. So therefore, this is defined in terms of formation of HI. But if we take the reverse reaction, that is what we call as dissociation of. Suppose look at this. This is enthalpy of formation of HI. Now take the other way. We are starting with HI gas. The on dissociation of this HI gas, we have half mole of hydrogen gas plus half mole of I2 gas. So this is what we call as enthalpy of dissociation of HI. We are dissociating HI to give you hydrogen and iodine. Then now look at it. The same species is formed in the first reaction, and in the second reaction, same species undergoing dissociation. Then this Laplace and Lavoisier law says the enthalpy of formation of HI will always be equal to the enthalpy of dissociation of the same species HI, but with opposite sign. So if this is energy releasing process, then this will be energy consuming process. So this is the meaning of the Laplace and the Lavoisier law. Then we have second law, that is Hess law of constant heat summation. Hess's law of constant heat summation. Hess's law of constant heat summation. This law says if a process is carried out in a single step or in a multiple step, initial and the final step being remaining same, either be carried out in the single step or in a multiple step, energy remains the same whether the process is taking place in single step or in a multiple step. According to this law, enthalpy change for a process remains same whether the process is taking place in a single step or a multiple step. So whether the reaction takes place in a single step or we carry out the reaction in a multiple step, the energy change will always be a constant. So the reason is, look at this, enthalpy. We use the term enthalpy. So the reason is why this process taking a single step or multiple step, energy change remains same. The reason is enthalpy is a state function. So this being state function, it depends only on the initial state and the final state, irrespective of the route or the path taken for this transformation. It is independent of the path taken for this transformation. It only depends on the initial and final state. So till the initial and the final states are remaining same, enthalpy change will always be a constant process. So suppose we have, look at this. This is the initial state. Now this is changing into the final state. This is the single step process. Single step process. For this, suppose we have this delta H. Single step. Now the same step is carried out in number of multiple steps. Suppose A is converted into C. Then we have C converted into D and D converted into final B. This is the initial state, this is the final state. In between these two we have intervening steps. Now for this A to C, suppose enthalpy changes delta H1, C to D delta H2, C D to B, suppose this delta H3. Then the net change. So if you add this 3, net change, C will cancel out, D cancel out, net change is A to B again. So therefore for this delta H total will be delta H1 plus delta H2 plus delta H3. Then according to this law, delta H for a single step, so this delta H will be equals to delta H T. So this is energy change for first one single step, this is for multiple step. So total energy change during the multiple step is summation of the energy change of the individual steps, delta H1, delta H2, delta H3, that is the total enthalpy change for this multiple step. So energy change are always same because the initial and the final states are same, and enthalpy is a state function. This is what we call as the laws of thermochemistry. So we have Laplace and Lavoisier law and the Hess's law of constant heat summation.